Hello everyone, my name is Muhammed Esgin, and I'm going to present you our work on practical post-quantum verifiable random functions and its application to Algorand. And as you can see in the slide, this is a joint work with various researchers. Okay, so VRFs have been introduced way back in 1999 by Michale, Rabin, and Wathan, and the main goal is to generate some secret-dependent random value in a verifiable fashion. And what this means essentially is that we want to evaluate a PRF function that has some secret key in it, and then we also want to prove that we have done this evaluation correctly. Okay? And these are very useful tools, and there are two most prominent proposals, one based on elliptic curves that is called EC-VRF, and the other one is based on pairings, which we call VLS-VRF. Okay? And the EC-VRF is used by the Algorand blockchain, and VLS-VRF is used by Dfinity. And these two proposals are quite nice because they do not require any heavy machinery, and they are essentially like some small extensions of the underlying like basic signature schemes, and therefore their efficiency is also close to the signature schemes. And they are actually, as I just mentioned, they are used in these blockchain protocols, especially proof-of-stake-based blockchains, and they serve like a verifiable way to input random values into the protocol. And this is kind of like the most prominent application of the VRFs, and therefore actually they have become very important tools, and they are also used in this DNS-SEC protocol. Okay, and you might ask, of course, why do we have this work if these tools are so nice? And the reason is because they are actually not post-quantum secure, because they are based on discrete log-like assumptions, which can be actually broken using quantum computers. Okay, to give you an idea of why we really need post-quantum security for VRFs, let's talk about how we use the VRF in the Algorand. And this will be kind of like a very simplified description. Let's first fix some notations. N will denote the round number, I will be the user index, and PIN will denote some stake-dependent threshold. And what this means is that if you have more stake in the blockchain environment, then this PIN value will be larger. Okay. Let's suppose we have some user Alice with some secret key SKI. And what happens in the protocol is that at every round n, the protocol kind of like receives some random value Qn. Okay, so for the purpose of this talk, you will just assume that this random value is some magically generated. Okay, so there are of course technical details of how this is supposed to be generated, but for our purposes, we just assume that this random value is given or kind of randomly generated at each round somehow. Okay, and we denote this by Qn. Okay, so Alice receives this random value, and then using her secret key, she takes this Qn as an input to the VRF function, and then runs the evaluation and gets an output that we denote VIN. And then she checks whether this VIN falls into the range starting from 0 up until PIN. And if that is the case, then she is the winner. Okay? And as you can see, the more stake you have, the larger PIN you will have, and therefore you have a better chance that you will be one of the winners. Okay, and of course, there can be multiple winners in the system. And what it means to be a winner is that so winners will run a voting protocol to choose the next block. Okay, so you effectively become one of the committee members that chooses the next block. And if we assume that majority of the stakes are held by the honest parties, then this protocol runs smoothly and everything works fine. Okay? But as we just described, if the VRF is not post-quantum secure, and if the adversary kind of gets a hold of like a scalable quantum computer and can compromise the security of the pre-quantum VRF, in this case, effectively every user becomes corrupted, right? So for example, if you imagine that you are using ECVRF and the adversary can break the discrete log problem, this means that the adversary learns all the secret keys, which means that any user becomes corrupted, okay? And this in turn means that the most fundamental security assumption is broken, which was that the majority of the stakes are held by honest parties, because so if you break the discrete log problem and if you're using ECVRF, for example, then everyone suddenly becomes corrupted, okay? And this is quite problematic because you can just easily create forks and even rewrite history. And the main reason behind this is there is no proof of work in the system. And once everyone gets corrupted, then it gets very easy to just create new blocks, because you are basically controlling the whole committee and you can decide what's going to be the next block. And you can make these decisions basically instantly because you don't need to do any proof of work. And therefore, you can even corrupt the users in the past or get their secret keys and create an alternative blockchain and instantly create many, many follow-up blocks so that you can actually kind of outrun the honest blockchain. Okay, because as I mentioned, there is no proof of work in this setting. So this means that the post-quantum security of the VRF construction is quite important even today, because I mean, you can even change what happens. So for example, if you break the VRF in future, you can even affect what happens now, okay? Therefore, it's an important issue. Okay, so let's now see the VRFs a bit more formally before we move on to our own construction. So we will have some function that generates the public parameters and another function that generates the public and secret keys of each user. And then more importantly, we have this VRF eval function that takes an input x and together with some secret key outputs a VRF value v and a proof of correctness, which we denote by pi. Okay, and finally, we have some verification function that checks that proof and the VRF evaluation is done correctly. And we will have three important properties from VRFs. One is kind of like a standard completeness property that is called provability, which means that the verification of an honest VRF run will succeed. And then we have the pseudo-randomness, which means that this VRF value v is pseudo-random. And finally, which is kind of like the very critical property, is uniqueness. And in particular, in the original work of Mikali et al., this corresponds to unconditional full uniqueness, which means that if you fixed any input x and a public key pk, then there will be only a single VRF value v for which valid proofs can be created. Okay, so the proofs can be created in different ways, but the VRF value will be unique. Okay, so this is a very critical property because we will rely on the fact that the users cannot generate multiple VRF values once the input is fixed. And you can actually see why this is the case from the Algorand application, because if you can actually evaluate in multiple ways, then this gives you more chance that you will be a winner. Okay, so this uniqueness is quite critical. Right, so let's now look at our contributions. So in this work, we introduce LB-VRF, which is the first practical post-quantum VRF construction. And this construction is based on standard lattice problems named module sys and module LWE. And as in the previous discrete log-based constructions, actually we built LB-VRF by extending it from a lattice signature. And the efficiency of our LB-VRF construction is actually close to this lattice signature that is based on the same assumptions. And thankfully, we do not require any heavy machineries. And most importantly, our proposal is much more efficient than prior post-quantum proposals. Okay, so I'm going to tell you more about this in the next slide. And then we use LB-VRF in the Algorand setting. And as we expect, the lattice signatures are much more communication costly than discrete log-based ones. And similarly, LB-VRF is, in terms of communication, is more costly than, let's say, like ECVRF. and therefore there is a drop in the throughput, but still we can maintain much higher throughput than Bitcoin. So I'll give you concrete numbers later on. And let's have a quick look at the efficiency. And so here we have EC-VRF, BLS-VRF, and LB-VRF. And as expected, the public key and the proof sizes are significantly increased, and the VRF value size is kind of okay. And in terms of the proof times, so again, LB-VRF is a bit slower, but we should note here that this is not an optimized implementation, and in the lattice setting, there are actually nice tricks that allows you to do much faster computation, and we haven't done these things. And the implementation is done using the Rust language. And for comparison, there are these two prior works that did show the feasibility of a lattice-based VRF construction, but unfortunately they do require very heavy machinery, such as constraint PRFs and exact lattice-based zero-knowledge proofs. So I'm not going to tell you what these things are, but these things are kind of not very efficiently instantiated. Okay, and in particular, the later construction leads to proofs in the order of megabytes, and actually they do not have concrete sizes in either of these two papers, but even the kind of like more basic proofs in the later paper, this YAZ plus 19 paper, even the basic proofs, they lead to proofs in the order of megabytes. So we can very likely expect that they cannot get below something in the order of megabytes. Okay, and our proofs, as you can see, is much better. And if you look at the kind of like the ordinary lattice signature, dilithium, which is one of the signature candidates in the NIST standardization process, and actually it's one of the finalists, one of the 3 finalists. The signature size of dilithium is about 2-3 kilobytes, and the public keys are 1 to 1.5 kilobytes, depending on the security level. And they actually use some compression techniques to bring down these numbers. So we can see that we are not too far away from these numbers. And if you compare to something in the order of megabytes, we are much better. Okay, so let's start talking about LB-VRF now. And before we move on to the kind of like the intuition behind LB-VRF, I'll tell you briefly about the 2 modifications that we need to do to the formal model. One is that uniqueness is computational in our setting, unlike the previous constructions which had unconditional uniqueness. But the uniqueness is based on the standard module sys problem, which is fine. And then we have a more restrictive pseudo-randomness property, which is few times pseudo-randomness, which means that the secrecy of the secret key is only guaranteed if you output a limited number of VRFs under a fixed key pair, okay, which means that you need to actually refresh your key pair from time to time. Okay, so I'll tell you why we need this. Okay, so to give you the intuition, let's first look at what does a Schnorr-like signature do. Okay, because the previous constructions built their schemes with their VRFs based on signatures, so it's good to understand what's actually happening in a Schnorr-like signature. So effectively, a signature sigma on some message M under a public key PK is like a proof of knowledge of some secret S, such that this S, if we commit to this S under some commitment key, then we prove that this is equal to the public key. Okay, so we prove that basically we know an opening of this public key PK. Okay, so here I'm actually kind of abusing notation because this S is not a message, but is actually the randomness of the commitment. Okay, and actually there is kind of like no randomness, sorry, there is no message in this setting. Okay, so in the standard discrete log setting, what we do basically is we prove that we know some S such that little g to the S is equal to the capital G, where capital G becomes the public key and little s is the secret key. Okay, so as I mentioned, there is no kind of message here, there is just one exponent. And with this, actually, we can, it's not actually too hard to construct a VRF from here, because we already proved knowledge of the secret key S. And what we can do is we can first derive a new commitment key from the public key and the message. Okay, so let's call this CK prime. And then we can just commit to the same secret key under this new commitment key and call the output as the VRF value. Okay? And again, in the discrete log setting, this means that we hash the public key and the message to some group element H, and we just compute H to the S, and that becomes the VRF value. Okay, so this is kind of like, again, the simplified setting, but this is kind of like the rough idea. And here, actually, we need to prove that these two S values that are used in two different commitments are the same, but this is quite easy to do. We just use the same proof response to prove their equality as in the standard EQ composition. Okay, so this is quite nice, and as you can see, we have just a few more steps in addition to an ordinary signature, and therefore these previous discrete log-based VRF constructions are quite efficient and quite nice. Okay, but how about the lattice variant? So what is the challenge that, or why can't we just do this in the lattice setting? And the reason is because the lattice signatures do not quite prove the same relation. They actually prove a relaxed relation. Okay, and in particular, it proves that we know some short alpha and S, which are some secret values, such that alpha times the public key is now equal to the commitment of S. Okay, so here we have this additional relaxation factor alpha in the relation, which makes things much more complicated. Okay, and this commitment scheme that we use in this setting is binding only if the input is short, which means that we cannot just simply divide both sides by alpha and say that alpha inverse times S is the opening, because that opening may not be short, because alpha inverse does not necessarily need to be short, and therefore that's not actually a valid opening. Okay, so we need to do actually something else. But let's first see what happens if we have two such proofs. Okay, so this means that in the first proof, we prove knowledge of some short alpha 0 and S0 such that this equation holds. Okay, and then a similar thing with some short alpha 1 and S1 such that the second equation holds. Okay, and note here that we do not have any guarantee that S0 is equal to S1 or alpha 0 is equal to alpha 1. So they can very well be different. Okay. Okay, so let's cross-multiply the two equations. So I multiply the first equation by alpha 1 and the second equation by alpha 0. And what this gives me is alpha 0 times alpha 1 times the public key will be equal to the commitment of alpha 1 S0. So I'm using the homomorphic properties of the commitment here. And then this will also be equal to commitment to alpha 0 times S1. Okay. Now, since the proof proves that alpha i's and s i's are short, their products, we can also guarantee that they will be short. Okay. Now that these inputs are actually short in the commitment and they are actually equal to each other, we can now run the binding argument and conclude that these two inputs must be equal to each other. Okay. So alpha 1 S0 will be equal to alpha 0 S1. Okay, and what this means actually that the ratios between SI's over alpha i's is actually equal to each other in both settings. And in particular, if I define this R as the SI divided by alpha I, then this will actually be a unique value for both executions. Okay, but note that R may not be short. Okay. So why don't we just then set, as before, we can first create a new commitment key CK prime and just commit to this R, okay? And say that the output E will be the VRF value. Okay, so here, of course, you may ask, okay, so you said that the commitment is only binding, if the input is short, but the input may not be short. So would this work? Well, actually it does work, because we actually don't need the binding property for this commitment here. Because the binding actually comes from the relation that depends on the public key. Okay? Because so here what we did is that for any two proofs that is generated, or that for any two valid proofs generated under the public key pk, for those two proofs, we will always have Si divided by alpha I as a fixed unique value. Okay? So you cannot find any other Si and alpha I such that like S0 alpha 0 is different than S1 alpha 1, because we just showed this in the previous argument. Okay? Which means that I actually don't need the binding in here, and I just compute the commitment function as it is without relying on its binding property. Okay, and the output will be the VRF value. Okay, so we have a more formal argument to prove that this is really the case in the paper. Okay, so this concludes the discussion of LB-VRF, and let's now look at the applications, and in particular the blockchain applications. And since we have this few time VRF case, let me first describe you how we kind of envision using LB-VRF in the Algorand setting. And in particular, I will focus on the one-time case. So let's suppose that this line denotes the round numbers, okay? And then we have some user that joins the system at round n. And what the user is going to do is to commit to some VRF public key that we denote by pk1. Okay, so what this commitment means is you just hash the public key and sign the hash, and you put the signature together with the hash value into the blockchain. Okay, so you have publicly committed to using this public key pk1 next. Okay, and this signature is just an ordinary signature. This is not the VRF, and this can be basically any long-term signature. Okay? And then actually we need to ask the user to commit to more public keys, like pk2, pk3 in the upcoming rounds, that I'm going to tell you why later on. And then we allow the user to use public key pk1 after some certain delay t, so starting from round n plus t. And let's suppose that the user wants to use the public key at some round n plus t plus I. And what the user is going to do is to send the public key, the round number where he committed to this public key, and the VRF output, which includes the VRF value and the proof. Okay? And what the verifiers will check is, what the verifiers will check that he indeed committed to this public key, and that the VRF output indeed falls into this state-dependent threshold. Okay? And so here, since now this public key is consumed, the user will actually need to commit to a new public key at this round. Okay? And here note that if the user does not really win this lottery that he is running internally, he actually does not need to reveal the public key or the VRF output, so he can still retain that public key and not use it. Okay? So he needs to publish the VRF output only when he is the winner. So therefore he can still kind of keep using the same public key until the point he publishes the VRF output. Okay? And whenever he publishes the VRF output, he needs to commit to a new public key. Okay? Okay, so let's now get back to the reason why the user needs to actually commit to multiple public keys. And this is because of this delay of t blocks that's basically the delay between the time that the user commits and the time that the user can start using that public key. Because if suppose you only commit to one public key pk1 and you consume this at around n plus t plus I, and if you want to be elected at round n plus t plus I plus 1 now, which is the next round, until after this point, then you actually do not have any other committed public keys that are basically T rounds in advance of this if T is more than 1. Okay. Therefore, we will actually ask the user to commit to T public keys so that he can basically start using the next public key, which is PK2, once he consumes PK1 in the next round, which is n plus T plus I plus 1. Okay? And here another thing is, since the users can commit the multiple keys, public keys on blockchain, we actually need to make sure that the users only have a single option for the public key that they can use. Because if we allow the user to have multiple public keys, then this actually kind of doesn't quite break the formal uniqueness property, but breaks the uniqueness that is expected in the application. Because the user has multiple choices for the public key, and he can choose to output the one that basically benefits his purposes. Okay, so therefore what we will ask the verifiers to do is to scan the basically rounds between n up to the time that the user is consuming that public key to make sure that there are exactly T commitments here and that the earliest one is being used at that round. Okay, so this makes sure that the user has only a single way to use the public key. So he cannot use PK2 here because basically the verifiers will notice that this is not the last one. Or if he says, for example, I actually committed to this at round n plus 1, then there will be only T minus 1 keys here. Again, the verifiers will reject this. Okay. So this is important in our setting. Okay. So to understand the efficiency impacts of the LB-VRF, so let's first break down the throughput of the original Algorand consensus protocol, and in particular we will look at the TPS, which is the transactions per second. Okay, so the main bottleneck in the protocol is this payload size, which is the amount of data transmitted every round between the voters, which is roughly equal to 5.4 megabytes in the original Algorand setting. Okay, and therefore we fix this payload size to be 1.4 megabytes. And then for Algorand, a block is generated about every 5 seconds. So we set the block generation time to be 5. And then when we were writing this paper, there were about 1,000 voters involved in the committee. So we fixed the number of nodes to be 1,000. And the total VRF cost, since it's using ECVRF, is equal to 80 bytes. And we assume that transaction size is equal to 1 kilobytes, and that since the transactions need to be authenticated using a signature, and since this is using a discrete log signature, the signature size we set is equal to 64. This is the original Algorand setting. And with all these things, we can compute the TPS of Algorand using this formula. And let me tell you what is happening here. So we have the payload size, and some part of this payload is occupied by the VRF proofs and the other outputs. Okay, so this is actually needs to be transmitted by the nodes or the voters. Okay, so we multiply the total VRF cost by the number of nodes. Okay, and then the remaining thing can be used for the transaction information, and the transaction information is transaction size plus the signature size. Okay, so this gives us the transactions per round. Okay, and if we divide this by the block time, then we get transactions per second. Okay, and if you put in these values into this formula, then we see that the Algorand protocol can achieve about 1,000 transactions per second, which is quite impressive. Okay. Let's now look at the setting if we want to integrate LB-VRF into the Algorand. Okay, so I have here the original formula for Algorand protocol, and let's recall how the LB-VRF Algorand worked. Okay, so what basically we were doing was that so every time we consume one public key, then we need to commit to a new public key. Okay, and here, along with sending the VRF output, which is the proof and the VRF value, we need to send the public key as well. Okay, and whenever we commit to a new public key, this also needs to be signed and put on blockchain. Okay, therefore we need to slightly change the formula. Okay, so since you only output or you only consume a public key if you are one of the voters, then this new commitment to the public key needs to happen, basically on average happens number of voter times at each round. Okay, and therefore in this formula we add the digest, which is the hash output, plus the signature size into the formula. And as we just said, along with forwarding the VRF output, the users needs to send the public key. So therefore this total VRF codes also includes the cost of the public key, which unlike the case in the original Algorand protocol. Okay, so now we can use this TPS2 formula to estimate the TPS for the LB-VRF Algorand setting. Okay, and we have done this with various signature schemes, and in here at the top we have EC-VRF versus LB-VRF together with various signatures. And again, you can see here that as we increase the number of nodes, the original Algorand protocol can still maintain 1,000 transactions per second. And here we have LB-VRF with different signature schemes, and in particular Dilithium, Falcon, and Rainbow are the three finalists in the NIST's post-quantum standardization process for the signatures. And we also have the discrete log-based signature here. And here are a few references that you can look at. And the full version of our work is available on ePrint. And if you have any questions, please feel free to email me. Thank you for tuning in.